Hello and welcome to our introductory lesson on PySpark. This session is designed for beginner data engineers and Python developers keen to explore the world of big data. We will embark on the guided journey starting from foundational concept of PySpark and its indispensable role in modern data processing. We will explore why PySpark exists, how it addresses the challenges posed by massive, fast moving, and often messy dataset, and how it empowers you to build scalable solutions. By the end of this session, you will possess a solid foundational understanding, enabling you to confidently approach big data challenges. So, what is PySpark? PySpark serves as a Python interface for Apache Spark. So if you ask what Apache Spark is, it's an open source unified analytics engine specifically engineered for large scale data processing. Imagine Spark as a highly efficient, super powered engine for handling immense volume of data across a cluster of computers. PySpark in this analogy is a steering wheel that allows you to control this powerful engine using Python code. Python's beginner friendly syntax combined with Spark's robust capabilities make PySpark an exceptionally accessible and powerful tool for big data tasks. In the realm of data engineering, we frequently encounter big data sets that are simply too vast and complex for single computer to handle. Traditional tools such as Microsoft Excel or even popular Python libraries like Pandas are perfectly advocate for smaller dataset but tend to struggle or outright fail when faced with big data. PySpark solves this problem by enabling distributed processing. It intelligently splits large datasets into smaller manageable chunks, processing these chunks in parallel across multiple machines, and then seamlessly reassembles the result. This approach makes PySpark incredibly fast, up to 100 times faster than older frameworks like Hadoop's MapReduce. Furthermore, it's fault tolerant, meaning if one machine in the cluster fails, PySpark can recover and continue processing without losing data, and it excels at handling real-time data streams. So what made PySpark so popular? It's the shift in data processing. The landscape of data storage and processing, particularly in data warehousing, has undergone profound transformation. The shift has accelerated by global events and relentless growth of digital interaction. Let's understand this paradigm shift with an analogy of a store. Let's say there is a store and the management demands daily, monthly, and yearly sale insight delivered via dashboards, KPIs, and predictive trends. In order to achieve this, a traditional setup was like when store close at 10 p.m., we run ETL jobs. What are ETL jobs? It's extract, transform, and load. What this job does, it extracts uneven or bad data from a database, transform it into a meaningful data, and load it into tables or a database. This meaningful data loaded in the tables is called aggregated tables. So these pipelines run overnight, and before 10 a.m., these aggregated tables are ready for business users, ensuring fresh data for decision making. It is efficient for manageable data volumes like in gigabytes. But after post COVID, the problems grew because data grew exponentially, overwhelming legacy system. Traditional ETL tools were on-premise servers proved slow, rigid, and expensive to scale. These ETL jobs failed frequently to complete on time, rendering dashboards useless. And this resulted a pivotal shift. Businesses were compelled to transition to cloud and big data technologies, embracing distributed computing frameworks like Spark. This move was driven by the critical need for scalability and ability to effortlessly expand processing power as data volume surge. Parallel processing, executing multiple data tasks concurrently for unprecedented speed, faster time to insight, delivering critical businesses intelligence in minutes, not in hours. This paradigm shift underpins the necessity of PySpark. It simplifies the development of scalable ETL pipelines for Python developers, directly addressing these modern data challenges. Now, let's understand the evolution of data infrastructure, data processing from on premise to cloud. This slide illustrates a historical evolution of data infrastructure from isolated on premises server to highly scalable cloud based solutions. Each stage represents a significant leap in how organizations manage and process their data. Let's start with the traditional ETL, which were running on on-premise servers. Initially, data processing was confined to physical servers located within organizations' premises. This setup was advocate for small datasets, typically ranging from gigabytes to few terabytes. These on-premise servers were scaled vertically, which involved upgrading single servers, CPUs, or RAMs. While straightforward, this approach quickly hit physical limitations. Other limitations were high cost associated with hardware upgrades and limited flexibilities, as organizations were bound by their own infrastructure. Then came a big data era. Data volumes surged into tens or hundreds of terabytes and even petabytes. Single servers could no longer cope with demands of storage and memory. Solution to this was distributed computing, the evident of horizontal scaling. Using many smaller interconnected servers become essential. Software frameworks like Spark emerged into coordinating tasks across these distributed environments. Hadoop, an early pioneer in distributed computing, Hadoop's MapReduce offered a batch processing solution but was often slow due to frequent disk writes. Then came Spark, evolved as a faster, more flexible alternative to Hadoop, leveraging in memory processing and robust fault tolerance. PySpark brought Spark's power to Python developers. The shift to cloud platform revolutionized data processing by eliminating need for organizations to manage their own servers. Cloud providers handle server maintenance, allowing organizations to focus on core development. Pay as you go model and auto scaling cluster optimized expenditure, growing or shrinking resources automatically with demand. Tools like Databricks, AWS EMR, and Azure Synapses seamlessly integration Spark. Tools like tools like Databricks, AWS, EMR, and Azure Synapse seamlessly integrate Spark with the modern data pipelines, simplifying big data operations for beginners. This revolutionary journey underscore why PySpark is crucial today. It acts as a vital bridge between a user-friendly Python programming language and the powerful distributed capabilities of Spark, making big data and cloud technologies accessible without a steep learning curve of complex low-level languages. So let's define data challenges. The definition of data challenges. Let's understand what big data is. Big data is not merely about sheer quantity of information. It encompasses data that is so large, moves so fast, or is so complex that traditional data processing systems are unable to handle it efficiently. It is the data that fundamentally challenges the capability of conventional ETL processes, relational database management system, or on-premise infrastructure. So, question is big data a problem or a solution? It is a problem that is effectively solved using cloud and big data technologies. There are three V's of big data. First V is volume. Data has grown from gigabytes to terabytes and now to petabytes. Traditional on-premise ETL system with their limited storage and compute capabilities simply could not cope with such vast dataset. Second V is for velocity. Previously, data was handled via daily batch loads. Today, data arrives as continuous stream via online sales, app clicks, IoT sensors data, demanding near real-time processing that traditional ETL jobs just cannot support. Then third V stands for variety. Earlier system dealt primarily with structured relational tables. Now data comes in diverse format. It can be JSON logs, click streams, images, videos, and social media posts. PySpark excels in this environment. Its distributed processing capabilities, built-in support for streaming data, and flexible data handling mechanism enables it to efficiently manage all three V's, making it an indispensable tool for modern data engineers. Now let's see all these three V challenges in more detail, starting with the first, which is volume. Volume, the first V of big data, refers to immense size of dataset that surpasses the capacity of traditional data processing systems. Your traditional RDBMS comfortably handles data volumes from gigabytes up to lower terabytes. These systems are optimized for structured data within the defined capacity. Now, if your data exceeds these thresholds of gigabytes, terabytes, then we can consider this volume as a challenge. Once your dataset reach tens and hundreds of terabytes or even petabytes, you're officially in big data territory. At these scales, distributing data storage and processing across multiple machines become essential. Let's see a real world example of such kind of data volume. A single Walmart transaction database can generate 2.5 petabyte of data per hour, reflecting its global sale operations. This sheer volume demonstrates the need of highly scalable data solutions. For Facebook, which creates 4 petabytes of new data every day, containing user posts, likes, comments, and interaction across its platforms. So, what is a thumb rule to know when the volume becomes a challenge? If your data set is so large that it cannot fit into the disk or memory of single server and therefore requires distributed storage and processing, you're dealing with big data volume. PySpark is designed to partition and process such data efficiently across numerous nodes. The second challenge, velocity, refers to the speed at which data is generated, collected, and must be processed. In the era of big data, the pace of data flow far exceeds capabilities of traditional batch processing. Historically, ETL processes operated in batch mode, running every few hours or days. This meant that insights were always delayed, based on historical data rather than real time events. Modern applications and business need demand near real time insights, often requiring data to process and analyzed within the seconds or minutes. This is crucial for timely actions like fraud detection, personalized recommendations, or dynamic pricing. Another real world example for data velocity is Twitter, which generates approximately 500 million tweets per day, translating to roughly 4,000 tweets per second. Real time analysis of this stream is vital for identifying trending topics and public sentiment. Another example is IoT sensors, which is connected to cars or industrial machineries, which can generate millions of events per second. Then there is another example, stock exchange, processes millions of trade per second. Even fractional delay in processing can lead to significant financial losses, emphasizing the need of ultra low latency processing. So, what is the thumb rule to understand when velocity becomes a challenge? If data arrives at such a rapid pace that traditional batch jobs are incapable of keeping up, and your business requires insight or actions in streaming or near real time, you are dealing with big data velocity. PySpark's structured streaming capability is specifically designed to handle these high speed data flows. Third challenge is variety. Refers to numerous type of data formats and the sources that modern system must contend with, moving far beyond the simple structured tables of yesteryears. Traditional system primarily handled structured data, which is neatly organized into tables with fixed rows and columns, much like spreadsheet or traditional relational database. Big data landscape now encompasses a complex of structured, semi-structured, and unstructured data. So if you define each type of this, so structured data are highly organized data that fit into the fixed field within a record or file. It has predefined schema. Semi-structured data is the data that does not conform to a fixed schema but contains tags or other markers to separate semantic elements, enabling some level of organization. Unstructured data has no predefined structure or organization. It's typically textual or media rich content that does not fit into relational database. So what is the thumb rule for variety? If your data pipeline need to process and integrate a combination of JSON files, system logs, various medias like video, audio, images, and relational data altogether, you're definitely dealing with big data variety. PySpark's data frames are incredibly versatile, allowing you to seamlessly work with virtually any data format in distributed manner, much like enhanced distributed version of pandas. So when does data become big data? There is no single magic number or threshold that definitively classifies a data into big data. Instead, it's contextual definition that depends on the capabilities of your existing tools and infrastructure. Data is considered big data when your traditional tools can no longer process it within the required time frame. You're compelled to migrate distributed and scalable system to handle the data's volume, velocity, and variety effectively. This is precisely where PySpark become indispensable. It empowers data engineers and Python developers to overcome these limitations by providing powerful, flexible, and scalable framework for processing vast and complex data sets, ensuring that insights can be extracted efficiently, regardless of data's characteristics. So, what are key takeaways from this video? To summarize it, PySpark is essential for big data because it acts as a critical bridge between Python and Apache Spark, enable you to process massive datasets efficiently across distributed computing environment. It is the go-to tool for modern data engineering challenges. Then the shift to the cloud and distributed system. Traditional data warehousing and on-premises solution are inadequate for today's exponential data growth. The industry has diversely moved towards scalable cloud and distributed technologies like Spark to handle volume, velocity, and variety. Then we have seen what are three V's. The big data is defined by its volume, its velocity, and variety. PySpark is uniquely equipped to handle all three, making it invaluable for complex data pipelines. I hope you all have loved this video. Stay tuned for similar content.